name is Mo Chen. I'm a scientist working at the University of Minnesota. And my background is biomedical engineering. And I use non-invasive brain stimulation, neuromodulation, and neuroimaging techniques to investigate neurological disorders, especially in spasmodic dysphonia. First, I'd like to thank NSDA for its support and Charlie and Kimberly to hold this fantastic event. And today, I will briefly report the progress of our research supported by NSDA. So this is our research team. Our lab is called Brain Plasticity Lab, and team leader is Dr. Teresa Kimberly. She is an experienced neuroscientist and physical therapist, studying focal dystonia for more than 10 years. And she is in Australia now for sabbatical leave, so she cannot come. And as the co-investigator of this research, I'll report the progress on behalf of her. And on our team, we also have ENT doctor with Dr. Scotty, who has more than 15 years of experience in Botox injection. He helped us to place the fine wire electrodes into participants' TA muscles. And his skill and professional skill and experience makes the procedure very smooth and easier. So, as Dr. Basson and Spurg mentioned, that spasmodic dysphonia is characterized by involuntary movements or spasms of one or more muscles of the larynx, and it is thought to be a neurological condition, which means if we want to study the mechanism of this neurological disorder, we need techniques to measure the activity of the brain. There are two widely used measurements that can measure the brain activity. So the first one is called Transcranial magnetic stimulation, or TMS. And the second one is functional magnetic resonance imaging, or fMRI in short. And TMS is a safe, non-invasive, painless procedure which allows researchers to measure the activity of portions of the brain. So when stimulating, an electric current is passed through a coil, and then the coil will generate a magnetic field, which can activate a small part of the area on the surface of the cortex. So in this way, we can map the brain to know where exactly controls the muscles in the larynx that are directly affected by spasmodic dysphonia. Also, we can use this to measure the excitability of that area to see what has changed in people in the brain in people with ADSD. And functional magnetic resonance imaging is another non-invasive tool to measure the activity of the brain. It works by detecting the changes associated with the blood flow, with the oxygenation level of the blood flow. When an area of the brain is activated, is in use, the blood flow increases in that area. So in this way, we can know exactly which area has been activated during a certain task, such as the EEG during the scan, and we'll know which area has been activated. It's related to that task and to that muscle being used. And or we can use that to scan the brain during resting. In that way, we can know which parts of the brain are activated, fluctuated synchronously. So in that way, we can investigate the functional network of the brain. And we combine these two techniques together by the neural navigation system. So we use neural navigation system to record the location of the TMS coil so that we know which exactly we are stimulating. And then we also use the task fMRI to measure the peak activation during the task. And then we can study the synchronization between the two locations in the resting state fMRI. So we designed a two-visit experiment. In the first visit, participants' brain images were collected, and in the second visit, the TMS locations were recorded, and the results were compared between the people with ADSD and those without ADSD. In the first visit, the task we designed was to make the formation of EEE during the scan and rest in a cycle again and again, so we can know where exactly it is activated. And in the two visits, fine wire electrodes, which are very thin, even thinner than a human hair, will be inserted into the TA muscle by Dr. Gali. And this procedure is very smooth, so that the muscle activity will be recorded by those electrodes. And our TMS coil was located by the imaging acquired in the first session, so that we know where exactly we were stimulating. And the picture C is the experiment environment. So we got interesting findings. So we know that, so now we have the two locations. The first one is the peak activation during the fMRI scan, which is the EEE task. And the second one is the TMS stimulation, is the TMS location. So here we can see the color means different colors means different individuals. So if they are the same color, that means they are from the same subject. And the circle here means the fMRI peak activation, and the triangle here means the TMS location. We can see they don't agree, they are not overlapping. There is a distance between them. This is very interesting. So which means during the task scan, the area of brain, one area of brain was activated. However, during the TMS task, which is directly stimulating that muscle, another part of the brain was activated. And we wonder what's the relationship, what the relationship between the two is. So we calculated the synchronization level between the two locations and to see how the functional connectivity between them performs, look like. So we find a very interesting phenomenon that you can see the red color means people with ADSD, and the blue color means people without ADSD. Each bar represents an individual subject, and the higher the bar is, the stronger the synchronization level between the two is. So we can see during the resting stage, in the people without ADSD, the synchronization level are pretty low, except one outlier there. However, in the people with ADSD, the synchronization level are pretty high. It seems like there is an obvious difference between the two groups. But during task, we don't see such an obvious difference, which is the right picture. So this may be indicating something that the abnormal connectivity is state. It is task related and state dependent. So during task and during resting, the synchronization level are so different in ADSD. So maybe this implicates that we may want to change our intervention strategy to aim, to target to modulate the resting activation pattern instead of to change the excitability, because the activation pattern, the synchronization level is different from the active excitability. we can have a very high excitability level there. However, if they activate very randomly, the two sides will not, so synchronized. However, even if you have a low level of activation, but these two spots activates in the same way, they have a very strong high correlation. So which means the synchronization level is very high. So previous intervention focused on suppress the activation, but our research may indicate that we may want to focus on modulate the activation pattern instead of the level of the activation, but how these two fluctuates. And this is just our preliminary findings. We haven't confirmed this finding yet because we are still recruiting. We haven't finished our recruitment. So we would like to thank all of our participants and the NSDA and all other organizations that support our result, and also Dr. Goding and Dr. Latlo. We are still recruiting, and your participation matters. So if you are diagnosed ADSD and you are interested in participating in our study, please do contact us. We do appreciate that. And I think our result will be very promising. And maybe someday we can solve this problem.